knows a lot about the science stuff. Professor Dave explains.
Now it's time to move on to an extremely important topic in organometallic chemistry. Cross-coupling reactions forming C-C bonds with transition metal catalysts have been known since the 1940s through the work of Morris Karash, a Ukrainian-born chemist working at the University of Chicago. Among his many contributions to chemistry, he noticed that aryl Grignard reagents give fair yields of biaryls when coupled with aryl bromides in the presence of trace amounts of transition metals. It was not until the 70s, however, that the modern cross-coupling reaction was born, using well-defined palladium homogeneous catalysts like palladium tetrakis triphenylphosphine. Now these reactions are one of the most important tools in the synthesis of fine chemicals and pharmaceuticals, and have been used on ton scale. The general mechanism of the cross-coupling reaction, with ligands omitted, is shown in this figure. Usually a pre-catalyst is used, largely because palladium-0 complexes are air-sensitive and difficult to use, whereas palladium-2 complexes are generally stable and not air-sensitive. Moreover, palladium-2 complexes are easily reduced in C2 to palladium-0 complexes, which then enter the catalytic cycle. The cycle is predicated on the ability of palladium complexes to easily alternate between two oxidation states, 0 and +2. Thus, palladium-0 complexes usually undergo oxidative addition with alkenyl or aryl halides, especially iodides and bromides, to yield an intermediate RPD2X complex. The halide is usually sp2 hybridized, although rare examples of sp3 halides exist and will be mentioned later. The halide can also be chloride, but this requires special ligands, and even fluoride, although this requires alternative metals. The oxidative addition step is common to all cross-couplings, but the transmetallation step can occur with a variety of metals, as we will see later. This is a nucleophilic attack of an organometallic reagent onto palladium-2 and replaces the palladium halide bond with a palladium carbon bond. The RPD-R' species then undergoes reductive elimination to generate the cross-coupling product as well as the initial catalyst palladium-0, which then re-enters the cycle. There are several classes of cross-coupling reactions, and they bear the name of their discoverers. The most popular version employs boron nucleophiles, usually boronic acids or esters, and is called the Suzuki coupling, or sometimes the Suzuki-Miyaura coupling, from the Japanese chemists Akira Suzuki and Norio Miyaura, who worked at Hokudai University and described the reaction in 1979. The Stille reaction uses tin nucleophiles, usually trialkyl stananes, and is named after John Stille, an American chemist who worked at Colorado State University. The Negishi reaction uses organozinc halides as nucleophiles, and is named after ei-ichi Negishi, a professor of chemistry who worked at Purdue University. The Hiyama reaction uses a number of silicon-based nucleophiles. It is named after Japanese chemist Tamajiro Hiyama, who worked at Kyoto University. The Kumada reaction uses Grignard reagents as nucleophiles and was invented in 1972 by Japanese chemist Makoto Kumada, working at Osaka City University. Kumada was a real pioneer in cross-coupling chemistry, having disclosed the first example of modern cross-coupling at the same time as French chemist Robert Corrieu. The first embodiment of the reaction used nickel catalysts, which are still used today, but it can also be carried out with the more common palladium catalysts. In cross-coupling chemistry, examples have been described where the nucleophile features essentially any kind of metal, including lithium, sodium, aluminum, zirconium, germanium, and a few others. But these are niche reactions not normally used in practical applications. In addition to halides, other leaving groups can also be used, first and foremost, phosphate and sulfonate esters. Suzuki and Negishi received a Nobel Prize for their fundamental discoveries in 2010. Of all the cross-coupling procedures, the most widely used today is the Suzuki coupling, which we will briefly describe in this tutorial. If one attempts the reaction of bromobenzene with aryl boronic acid in the presence of a palladium catalyst, there is no product. Suzuki then discovered that the coupling occurs in the presence of hydroxide ion. One can run the reaction in two phases, with a strong aqueous base and the reactants in an organic solvent, or under homogeneous conditions, in a dipolar solvent like dimethylformamide or dimethylacetamide, and a soluble base like tetrabutyl ammonium hydroxide. Under these highly basic conditions, with pH typically 11 to 13, the reaction occurs smoothly. Given that aryl boronic acids are Lewis acids, hydroxide ions react with them to form, at equilibrium, a borate species. Suzuki proposed that this compound is the nucleophile that performs the transmetallation. On the other hand, hydroxide ion also replaces the halide in the palladium coordination sphere, yielding, at equilibrium, a PDOH species. Might this species play a role in the transmetallation as well? The first confirmation that this is the case came from John Hartwig, currently a chemistry professor at UC Berkeley. He showed that the reaction between 6 and 2, run in THF and water, is about 10,000 times faster than that of 5 with 4. Therefore, it appears that, at least under these conditions, the borate species 4 is not the active transmetallating agent, and if the neutral boronic acid is the active species, too much hydroxide, which converts the active 2 to the inactive 4, may inhibit the reaction. This was indeed demonstrated by the group of Christian Amatore and Annie Jouton at the École Normale Supérieure in Paris. The kinetic law shows a maximum rate at intermediate pH. Too high a pH inhibits the reaction by forming borate 4, whereas too low a pH also slows down the reaction by not forming enough 6. The optimum pH depends on the acidity of the boronic acid and on the position of the equilibrium between species like 5 and 6. Much more synthetic and mechanistic work has been carried out on this important reaction than we are able to describe in this tutorial, and it is possible that borate species 4 may play a positive role in some versions of this reaction. One of the most significant developments of the last 2 decades has been the replacement of the old-fashioned triphenylphosphine ligand with a variety of bulky electron-rich ligands, which afford much more robust and efficient catalysis. Some examples are tri-tert-butylphosphine, tricyclohexylphosphine, and biaryl ligands, often called Buchwald ligands, like S-phos. The latter were invented by Professor Stephen Buchwald at MIT. From a synthetic standpoint, the Suzuki coupling is very general, and literally thousands of compounds have been prepared by this methodology. However, when compared with other cross-coupling reactions, it is important to highlight some limitations. The most obvious drawback is that it employs highly basic protic conditions. All functions that can be hydrolyzed, such as esters, are potentially labile under the conditions used. Any acidic CH bond can in principle be deprotonated, potentially leading to epimerizations or racemizations. Boronic acids can be proto-deboronated under basic conditions, and this means an excess of boronic acid must often be used. Another one of the limitations of the original Suzuki coupling is its inability to couple sp3 hybridized halides. This has been overcome by way of nickel catalysis. Alkyl halides can be generally employed with a number of boronic acids using a nickel-0 precatalyst, and a number of bidentate nitrogen-based ligands. In this field, the key figure has been Professor Gregory Fu at the California Institute of Technology, who has even reported examples of enantioselective couplings under nickel catalysis. A simple example is shown in the scheme here. The main limitation towards the general application of nickel chemistry is the poor mechanistic understanding of the reaction. There are clear indications that, alongside the classical mechanism shown for palladium, a nickel-1, nickel-3 mechanism also operates. In addition, the amount of catalyst needed to perform these reactions is often in the range of 5 to 10 mol%, against 1 mol% or less with palladium. As a consequence, the nickel-catalyzed coupling is an area of intense investigation. It is possible that in the future, scarce and expensive palladium will be routinely replaced by cheaper metals, like nickel or cobalt, for an environmentally more benign cross-coupling, but this area still needs a lot of development. Even with the current limitations, the palladium-catalyzed Suzuki coupling remains the most popular CC coupling reaction in all realms of synthesis, including real-life applications of pharmaceuticals and fine chemicals.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.